6 of the groups. We have decided to previously we just followed the book, but this time as we are taking the online classes, so different teachers will prepare different
Slides.
presentation, yeah. So it has been prepared by your Farhad sir. So let's see. Okay. So in this course, I and my colleague Arif Hussain will be there. Okay, here is just a time outline. We will try to follow this one. I do not know whether it will be possible or not, but
Sir, what is BIU description?
yes, everything you'll know. So today what we will discuss, basically everything, just the I should say what we will discuss, these things has been given here. So obviously you will know what is BIU and everything. So let's see, there will be 5 minutes break, obviously, if to, and I will ask everyone to give attention actually, because you will learn so many new things today, because this is the first lab. So various new things will be there, and I will ask different person, and I will ask to help me from maybe from the starting or from the end. I have the student ID with me, so you just help me. It is nothing like that. If you do not get to answer, so that is not a problem, but just try to be with me. So basically we'll start from this simple diagram. So previously I have said that CPU is the mastermind, or he is the principal element of a computer that you have. So we have microprocessors there. So microprocessor is the only element that can actually that can process things, that can take decision, and all other things, the memory input output devices, are the things that are helping the CPU to do those works. So in the last day I have okay, in the memory part, you have basically RAM and ROM part. You know what is RAM and ROM?
Yes, sir.
Yes.
Random
So
access memory.
yes, that means one is permanent. That means that is only read only.
Yes, sir.
We can only read from there. And RAM, we can actually change the values, and whenever the power is off, maybe all the values from the RAM is deleted. So basically RAM memory is RAM and ROM, and we will see different divisions. Maybe we will concentrate on the RAM portion today, and few segments of the RAM portion. Maybe we cannot cover all those things, but basically in the memory we basically keep the program data and other data, like that can be anything, that the file to read, and like the applications that you have are like the program data are saved there, or that can be programmed, and other data is also saved in memory. So whenever CPU needs, so it can access those program data and can execute. Is it okay? And in case of input output devices, I have said in the earlier class, like the keyboard is a input device. I've just given an example, and the printer is output, or a monitor is output device, isn't it? So input device and output device. So what we will do today, we will try to learn about the memory part, few things about the memory, how that is segmented, how that is what is the structure of the memory of 8086. And also the second thing that we'll see, now we're seeing the box here, and in the second part of the class we'll go inside the architecture of 8086. Okay, so the main purpose of CPU, basically, if we say what does a CPU do, if you say what does a CPU do, that basically do what? It fetch, decode, and execute. So it fetch the program data, it fetch the program I have said before that all the programs are saved in machine language. That means 1 and 0, isn't it? So what does a machine do? It fetch from the memory. Whenever we write a command in your emulator or in assembly language, then whenever it will be executable, that will be saved in the memory. So whenever you ask the CPU to run that program, so at that time that will fetch the machine language that has been saved in the memory. Then you can see here there is a connection between memory and CPU. So it will take the data from memory, and that is called fetch, and then it can be decoded. It is decoded inside the CPU and executed inside the CPU. Is it okay?
Yes, sir.
0909. Can you hear me? I'm starting from the beginning.
Yes, sir, I can hear you.
Is it clear? Is it clear to you?
Yes, sir.
No, I'm asking 09.
Yes, sir, I can understand.
Okay, okay. So now you can see to communicate with CPU, the memory and input output devices. So 09 with I ask you till I go to the next ID. You just respond, and whether you have understood or not, just let me know. Okay.
Yes, sir.
Okay. So you have a CPU and memory. I do not know how much time will it take, but you obviously try to remind me. Okay. So we have CPU and memory to you can see, okay, obviously when you say address bus, data bus and control bus, what are they? We do not know. So just a overview, the address bus sends out the address. Okay, what is bus basically? You can say it is a just it is a terminology by which we can say that there is a connection, there is a connection between CPU and memory. It is called communication highway sometimes. So basically the address, with the address bus, CPU sends the address, sends out the address, and with the data bus, we will go in details maybe later on. The data bus, it exchanges the data, and with the control bus, it sends the signals, control signals to different position. And here you can see the data bus is basically bidirectional in both the cases, and control bus and address bus, those are only sent from the CPU. And data bus, so from CPU we can write something to the memory, or we can read something from the memory. Is it okay? 09. What is write and read? So when we transfer something to the memory from CPU, what is that? Write or read?
Right.
Right. And when you read something, obviously that suggests that we are reading from the memory. So same thing goes for the IO ports. Now, talking about, whenever we're talking about the address, so let us say in South Hall level 1, you have 4 rooms here, and A, B, C, D are the people who are residing inside there. So if I say, who are residing inside 103? So what will be the answer? 09.
IJKL.
IJKL. That means this is your address and this is your content. Is it okay?
Sir. Yes, sir.
This is your content and this is your address. So where, that is address, and who and what, that means that is the data. So I have already said IJKL. Is it clear? So I am going to the next ID, 13. 13.
Yes, sir.
Okay. Have you understood up to this?
Yes, sir.
Okay. Now, these addresses, in case of memory, addresses also expressed in terms of zeros and ones. So you already know about bit, isn't it?
Yes, sir.
Okay. What is a bit? That means 1 bit. That means it can be either 0 or 1. So if a address is of 1 bit, what does that mean? How many address that can that have?
1.
So address is 1 bit. So how many possible combination
2.
is there of zeros and 1 in 1 bit?
2.
2. That means 0
and 1.
So with 1 bit address, you can basically do what? You can actually have 2 addresses, isn't it?
Yes, sir.
And whatever data, we are not saying anything about the data, but whatever there is inside the address, if it is 1 bit, then we can have 2. So if we have 2 bits, how many address can be there?
4.
4. Okay, before going to there, so from the CPU we can select. So if we want to read something, I think read and write is clear to all of you.
Yes, sir.
So yes. So whenever you want to read something from the address or from the 8086 memory, or the memory that has been connected here, so CPU can select from this side. Okay, from this side I want to read, or from this address I want to read. So it can select 0 or it can select 1. So that will be selected. The address, I have said through the address bus, the CPU sends out the address. So whenever it sends out the address, that address will be selected. That is the thing. Is it clear? 13?
Yes, sir.
Okay. So for 2 bits, we have 4 possible combination. Already she has said, and you can see 0001 1011. And also if you see the addresses, just to visualize. So from the CPU, let us say this is your address bus, and from the address bus with a say, you can say a mask which can select either of these among these 4, it will select only 1 depending on the address. Okay. So basically with the address bus, CPU sends out the address. That is the thing. So we can see 4 address can be selected. So if you have 3 bits of if our address bus is of 3 bits, try to understand our address bus is of 3 bits. So how many combinations?
Sir, 8 combinations.
8.
Sakib, I'll come to you later. So let her give the answer. Okay.
8.
So 8. Okay. In this case, we can move to different. We can select, the CPU can select different locations. Is it okay? Now, in total here. So if we get the summary, 1 bit, 2 bit, 3 bit. How many addresses? 2 addresses, 4 addresses, 8 addresses. So here we have 2, we have 4, we have 8. So if we have 20 bits, how many addresses will be located? How many addresses can be there?
2 to the power 20.
2 to the power 20. That means if we have 20 positions, so it is your first position, second position, it is 20 positions. Each position can be of 0 and 1. So the total combination is 2 to the power is 20, isn't it? So
Yes.
basically your address bus of 8086 is of 20 bits. So how many addresses are possible in 8086? How many addresses are there? That is 2 to the power 20.
20.
Is it clear? 30?
Yes, sir. Yes, sir.
Okay. Then I'll ask 16 to take over. 16.
Yes, sir. Yes, sir.
Okay. Yeah. Is it clear up to this?
Yes, sir.
Okay. So in 8086, the addresses are in total. We're discussing about a few of the. We'll discuss about the memory. How many addresses are there? That is the summary of the last few slides. Okay. So here 20 bits. That means in binary, it starts from 20 zeros, and with the combination, after doing all the combination, it will go up to all ones, from all 0 to all 1. So that is 2 to the power 20 addresses are here, isn't it?
Yes, sir.
Now, just to sometimes we actually in the memory they are represented in binary, but for our convenience sometimes we express those addresses using hex. You know about hex number, isn't it?
Yes, sir.
Okay. So if it is 5H, that can be 5H means it is in binary, it is 0101. Then 1001, that is in binary, and in hex it is this. So from 5, and it has been given up to 11. So tell me 34, isn't it?
No, sir. 16.
16. Okay. 16. So what will be the address in hex in this position? I want to express this binary number.
FH, 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 FH.
So what does that H means?
It is
16.
Anyone other than him?
Sir, I think H means hexadecimal.
Yes. That means if you want to express, like if you say like 0AH, that means it is saying that it is a hex number. Like if you have 2 or 3, like it A5, you are writing 5. So without writing the H, so
I will
you
not
cannot,
figure it in. Yes, sir. In
you
which
cannot say
number
that it is
system?
hex or yes. So if it is like 5D, that means it is decimal. Or if you do not write anything, so decimal. So if you do not write anything, that will say that okay, this is only 5 in decimal. So 5 and then when you are going to 10 and 11, you can see that in that cases it is A, B, C, D, E, F, isn't it? So why we have transferred to hex? Maybe in another class we have decimal number system already practiced everywhere. So why we are moving to hex in case of computer computing? So there is obviously explanation for that one. We have 4 bits, so we can have in total number of combination can be 16. So we have chosen another 6 from 0 to F, so that all those bits can be utilized. That is the thing. Okay, that is another part, but we can express the addresses in hex. Is it okay? 16.
yes, sir.
Now, so what will be what is the binary then? F. That means there are 5 Fs.
Yes, sir.
Each of them can be 1 F is nothing but
4,
1. So in 5 Fs, that means you have 21. That means that is giving you the hex number. Okay.
Yes, sir.
So it starts from 0. So you can see that if we write the addresses of 8086, that is basically a 5-bit of hex numbers.
Yes, sir.
So basically we call it physical address. Physical address. Okay, I'll come to that point later. Just try to remember, it is called the physical address of the memory of 8086. So if we just give a recap up to this, basically, okay, it is difficult to give the recap. So basically, we have tried to show you about the give you an idea about the address of 8086 here. So there's 2 to the power 20 addresses because 8086 have 20 bits of address bus. So it can locate or it can address 2 to the power 20 addresses. Okay. Now in we're moving to learn about few things about the machine language. So how high level language is converted to in the previous class you have said about the compiler. So can you remember 16?
Yes, sir.
High level language like MATLAB, Python, all those things has compiler. Those compiler actually translates the high level language to machine language. Can you remember?
Yes, sir.
Okay. So in our case in assembly language we have the software emulator. Maybe all of you have by this time. So assembly language we have assembler. We have assembler to assemble or to translate the assembly language into machine language. Is it okay?
Yes, sir.
Okay. So now here you have a code. So do not bother about what are the syntax written here. I'm just saying that move is something like that. You want to move something. You want to copy something from somewhere. So 05H, by this time you already know that what is 05H? It is a number, isn't it? So it is a number 05H. That means in hexadecimal it is 5.
Yes, sir.
And you want to move to a register. Okay, I will talk about register later. Register is a temporary memory, I should say. General purpose registers are one of them. AL is a temporary memory which is inside the 8086 memory. Try to remember, memory is outside the CPU, but these registers that we are showing here AL, BL, all these things are inside CPU. Okay, forget about that one. Just remember this is a memory location inside 8086, and we try to copy 05 to there. So we do not know. We have written this one in assembly language, isn't it? This is
Yes.
the
Can you
code for
repeat this
assembly.
part again? Can you repeat this
Uh-huh.
part? Can you repeat this page again, sir?
Okay, obviously. So what I try to say that do not it is not needed. You need to understand the code, but try to have an intuition that the move portion that in the code, that is basically that will copy something to somewhere. That is the instruction that will take some value to somewhere. So the instruction says that the okay, first one is your source. First one is your destination where the value will come, and this is your source. So that means 05H will be moved to AL. AL is a register. You will many a time you will come to that term register, and we will discuss about that later. Try to remember this is a temporary memory inside CPU. So if you have a no, sorry, I do not know whether we have here. Okay, you have CPU, then input output, and then memory, isn't it? So inside that CPU,
Yes,
we have
sir.
some temporary memory. So among we have few names. So AL, BL are a few of them. Okay. So this is not the
Yes,
memory.
sir.
Okay, it is inside the CPU.
Yes, sir.
So whatever. So we have the assembly language here. So how the and the machine in the machine language. So this move AL and 05H can be is stored like this, zeros and ones. So
Yes,
here
sir.
is your, is it okay?
Yes, sir.
And
It is
this
okay, sir.
move BL is stored like this, zeros and ones. And add these two is, okay, I have gone to 16 after, have I changed from 16?
No, sir.
No, sir.
Okay, okay. After 16, who is there? 33. 33. Can you hear me?
Yes, sir.
Okay. Have you understood up to this? Huh?
স্যার আরেকবার বললে ভালো হয়।
Okay, what from where actually you have understood this portion, isn't it? Emulator part, that this is a code. Have you understood this is the assembly
Yes,
code?
sir. Yes, sir.
Okay, from there actually what we try to do, that this is a code, and we're trying to translate that. Just you do not need to know that how this format came, how this 1010 came. Just try to get that a machine language of one code can be translated to 1010. Is it okay?
Yes, sir.
Okay. So all these codes can be translated into machine code of zeros and ones. That's what I tried to say. Okay. So whenever these are translated in machine language by the assembler, after translating to machine language, it basically it saves into different addresses. Just get 33. Okay, whenever I'll ask someone, so you can put your microphone on so that you can directly answer. Okay, so whenever we have assembler here, assembler translates this code, that means the machine code, to the assembly code to machine code. After translating, it saves that code into the addresses, into different addresses in the code segment. Obviously we will go to code segment and things there. So this is your different address, and here what is the it is considered 2 to the power 3 for simplicity. For simplicity we have kept only 3 bits, but basically all these addresses in 8086 are how many bits? 33. How many addresses are there in 8086? 33. Can you hear me? Okay, anyone other than 33?
Sir, 2 to the
Huh?
power 20. 2 to the
2 to the
power
power
20.
20. Yes, 2 to the power 20. That means we are considering, just for simplicity throughout this slide, we will consider this 33 bits of addresses, but you need to remember in 8086 we have 2 to the power 20 bits of addresses. Is it okay?
Yes, sir.
And get this thing clear, the address bus is of 20 bits. Address bus is of 20 bits and number of addresses are 2 to the power 20. Do not get confused between these two. Okay, I think it is clear up to this. So all these 6 machine codes, those are saved in different positions in the memory. Is it okay? Have you understood? 33.
Yes, sir.
So now I should write this one, that your 8086 or in the memory, sorry, in the memory addresses stores, each address stores 1 byte of data. Each address stores how many bytes of data? 33. Huh?
1 byte of data.
Okay, so 1 byte means how many bits?
Sir,
Anyone other than 33?
Sir, 8 bits, sir.
8 bits.
sir, 8 bits.
Sir.
Okay. So 1 byte means 8 bits. So in the address, you can see we have 8 addresses, and here all of them are 1 byte of data. So basically, this memory is 8 bits of memory. Like all the address contains 8 bits of data. Is it okay?
Just
Now-
a second, Robiul.
হ্যাঁ,
Yeah, slide number গুলো দেওয়া যাবে। Insert slide numberটা দিয়ে দে তো।
আচ্ছা, how to from here এখান থেকে দেয় নাকি?
না এখান থেকে না, তুই তোর ব্যাক করতে হবে। ব্যাক করে ইনসার্টে গিয়ে যে স্লাইড নাম্বারটা দিয়ে দে একটু।
Okay, so from insert slide number. Just a minute. Yes, I think it is visible now.
হ্যাঁ হ্যাঁ, ওকে।
Okay, so 1 byte of data, so that is 8 bits. So sometimes we call the upper four bits as upper nibbles and lower four bits as lower nibbles. So those are just names. We have 8 bits of data, and then we have, so it's 16 bit. How many bytes? After 33, who is there? 34. 34.
yes,
Can you
sir.
hear me? Yes. So
Sir, before answering, I had a confusion. So can I just ask you?
yes, obviously.
Sir, previously you said, sir, the address bus consists of 20 bits, right? So in
Yes.
order to that, there has to be 2 to the power 20 number of total addresses. But now you're saying, sir, the address is actually storing 1 byte of data. The previous
Yes.
example. So
Yes.
there is at 2 to the power 8 total addresses according to that estimation. So it's a bit contradictory because
No.
previously-
Okay. Just I got your answer. So don't know. I can go to that slide. Okay, I do not. Just get this point. In all the rooms, you have 101, 102, let us say in South Hall. So it is fixed that how many people will be inside that room. Is it okay?
Yes, sir.
There are 4 people. There will be 4 people in each room. But how many rooms will be there, that depends on another factor. That depends on the address bus. Is it clear?
স্যার
So,
এই
sir-
পার্টটা আরেকটু এক্সপ্লেইন করলে ভালো হয় স্যার, মানে এটা একটু কনফিউজড।
Sir,
Okay, okay.
sir, so if I understood it right, there is going to be 2 to the power 20 number of rooms according to your statement, and
Yes.
each room will have 2 to the power 8 address.
No. Just this data, the addresses combination, we are not talking about the address combinations. So you can say that, okay, our address combination is 2 to the power 8. But what, so do we not need that one? Because you have a movie, or you have a video in your hand, or you have a Word file. So whatever you have, that data, so that will be within that 2 to the power 8 combination. But we do not need that one. But for addresses, we need the locations for which we are considering 2 to the power 20. Is it okay?
Yes, sir. No.
So for content, we do not bother about what is. It is obviously within the 2 to the power 8 combination, but we do not need that one. We do not need that combination. When it can be same, all of them can be same. Is
Yes,
it
sir.
okay?
Yes,
The
sir.
data can be same.
Yes, sir.
Okay. I hope that all of you have understood up to this. Okay.
Just a second. I think what you guys are getting confused is between address and data. Those are 2 different things. Okay. Address bus, that is 2 to the power 20. That means how many addresses you can have. It has no relation with what you will have within that address. That means what will be the data that is not related with 2 to the power 20. Okay. Data is a different thing. Address is a different thing. Address bus is 2 to the power 20. That means that number of addresses you can have. But within that address, what you will have is a completely different thing. I mean, don't get confused between these 2 things.
Yes. Thank you, Arif. So so if we have now, can I move forward? 34. You
Yes,
keep
sir.
answering. Okay. So we have 16 bits. Now we have 2. So that can be in 8 bit. That means 2 bytes, isn't it?
Yes, sir.
16 bit means 2 bytes. So 2 bytes, we call it 1 word. Is it okay? We call it 1 word. So here it is 16 bit data. So the lower, each of them is 1 byte, isn't it?
Yes, sir.
So we call it upper byte and lower byte. You
Yes.
need this on upper byte and lower byte, and upper nibbles and lower nibbles. So in previous case, it was upper nibbles and lower nibbles consisting of 4. And here you say upper byte and lower byte. Now, sometimes you get confused what is 1 GB of memory. Sometimes you buy from your operator. Different operators are there. So sometimes we can see it is 1024 bytes. So how those things comes? Let's see. Just do not get confused to that. So you know that it is 2 to the power 1 for if we have addresses of 2 like. If we have 1 bits of addresses, address bus, 2 bit of address bus, 3 bits of address buses. So now here you can see 2 to the power 5, 2 to the power 6, it is 64, 2 to the power 7, 128, 2 to the power 8, 256. And then whenever we reach at 2 to the power 10, then what is 2 to the power 10?
1024.
1024. That means whenever we reach, this is the rule you need to know, that we sometimes whenever we count our currency, the taka, what we do, 100, then 1k, then 1 lakh, then you go for 10 lakh, then something like that. So or you go for million to billion, trillion, all those things. But here in this case, whenever there will be a change in this 10, whenever it will be 20, whenever it will be 30, this k value, it will be mega, it will be giga, it will be terabyte. Is it okay?
Yes, sir.
Yes,
Have you understood? So each of these addresses basically have 1 byte of data. That's what we are saying, 2 to the power 20 bytes, 2 to the power 20 bytes. Sorry, 2 to the power 4 bytes. That means 16 byte, and it is 1 kilobyte. That means 2 to the power 10 means 1 kilobyte. So if we go for let us say to the power 13, so what can we do for that one? So we can rewrite to the power 3 into to the power 10, isn't it?
Yes, sir.
So what is to the power 3?
8.
8. So that can be written as 8k. Is it okay? 34.
Yes, sir. Yes, sir.
You keep responding, okay? And whenever we reach to the power 20, so every time it is increasing, you can say 11, 12, 13, then whenever it comes to 20, so it is basically to the power 10 to the power 10, it is, we call it 1 megabyte. 1 megabyte of memory. 1 megabyte of memory.
Yes, sir.
So again, same thing, whenever you go from to the power 30, that means 1 gigabyte. So this time I can ask randomly 118. 118. Can you hear me?
Yes. Yes, sir.
So if we have a address of to the power 26, how can we express this value in terms of gigabyte?
In terms of gigabyte.
Yes.
Sir. Okay, 1
Gigabyte or megabyte?
So megabyte. So it
Two,
can
oh,
be
sorry. In terms of megabyte. Sorry.
so
Sorry.
it will be 6 megabyte.
6 megabyte.
Yes.
Wait. Explain how 6 megabyte. Just explain.
Sir, in 2 to the power 26, we can write as 2 to the power 6 into 2 to the power 20. So
Okay.
2 to the 20 we can write as 1 megabyte, and 2 to the power 6 will be 6.
2 to the power 6 will be 6.
Yeah, how 2 to the power 6 is 6?
No, sir, it won't be 6. So 2 to the power 6 will be 64 megabyte. Sorry, sir.
So it is 64 megabyte. Have you understood, everyone? 34. Can you respond?
Yes, sir.
34.
Yes, sir.
Okay. I think this is clear to all. If you have any question, you can ask from here. Okay. Before going to read write, what we have learned about the memories. So before we have learned about the 20 bits of memory and how those memory saves the how those addresses saves the data of the program. Then we learned about a different bits and bytes combination, like how many bits is a byte, how many byte is a word, and what are they called, upper nibble, lower nibble, upper and all those things. And also we have learned about how to represent in megabyte, gigabyte, and kilobyte things. So basically, your 8086 is. So tell me, what is the memory? What is the size of the memory of 8086? 88. Can you hear me? 88. 88.
স্যার 88 স্যার একটু কাজে গ্রামে যাচ্ছি স্যার।
ও আচ্ছা, ওকে।
মানে এই জন্য
বাসে
একটু প্রবলেম
বাসে
আছে।
বসে ক্লাস করতেছে নাকি?
মানে স্যার জি স্যার, মানে স্যার রেসপন্ড করতে পারবে না।
ওকে ওকে ওকে। সো কায়েস 91 91 91. So obviously, whenever I will ask randomly, that will be your class performance. When I come to serially, maybe that can be considered, but when I ask randomly, that is the thing that whether you are present in the class or not. 92.
Yes, sir.
Can you
Yes,
hear
sir.
me? 92.
Yes, sir.
So what is the memory size of 8086?
1 megabyte.
Okay. So that's the thing. That means you have 2 to the power 20. That means it is 1 megabyte. Yes.
Yes, sir.
So now we'll see. I have said that before going to the next part. Basically, we'll try to see the read and write operation. Is it okay? So we'll see how the CPU reads something from the memory and writes something to the memory. So basically, this is the figure that you have seen before. So let's go to the next slide. Now we want to see the read operation. So the slide is self-explanatory. So I'll just go on. Maybe once it will be okay. So to read something from the memory, there are 3 steps. Who is responding now? Now
Sir, 92 is responding now, sir.
No. That was random. So 48. Are you there?
Yes, sir. Yes, sir.
Yes, 48. So you just keep responding, okay?
Okay, sir.
Okay. So for read operation, we have 3 steps to read something from the memory. I'll show step by step. So the first step is the CPU will send out the address. So through the address bus. So first address will be sent through address bus. Then second, that means that will be selected. That means whenever we'll say 10, and obviously I'm saying for simplicity we're taking 2 to the power 3 memory addresses for simplicity, but in real case it is 2 to the power 20. Okay, whatever. So in CPU we have 100. That means this will be selected. Is it okay?
Yes, sir.
48. Keep your microphone on, okay, so that you can respond quickly.
Yes, sir.
Okay, so this will be selected. In the secondly, the control bus will send the so first thing, address bus will send the address, then the control bus will send the signal that I want to read something to the memory, that I want to read something. So first thing is address sent by the CPU to the memory, that address will be selected, and then the signal will give the read command, and thirdly that data, after getting that command from the control bus, that data will go to the CPU.
Yes, sir.
Great. Have you understood?
Yes, sir.
Can you repeat?
Okay, I can repeat obviously. So we have 3 steps. First step is CPU sends the address from where it wants to read something. Huh?
Sir. From the address bar. Yes, sir.
From the we want to, let us say we want to get the content. Do not get this content. We want to content of this address.
Yes, sir.
We want the content of this address. Address bus sends the address.
Yes, sir.
Controls bus sends the signal that I want to read.
The data of that address.
Then third time, that data will go through the data bus. So in 8086, a data bus is of 16-bit, but for the simplicity, we're just keeping that 8-bit of data bus. So I'll discuss all those things, which bus is how many bits. We'll discuss that later. So here, this data will go to the CPU. Is it okay? The read
Yes, sir.
operation? Okay.
Yes, sir.
So, oh, sorry. Then in the write operation, so the same configuration. Now I want to write to some address. Is it okay? I want to write something to some address. That means I have a content. This is my content, and I want to write to some address of this. That means here is 6 address. I want to write this address. I write this data. This is your data. I want to write this data to any one of these 6 that will be set by the address bus. So there are 3 steps, but there is a bit difference. Okay. The first step is same. It sends the address from the CPU. From the CPU, the address has been sent, and that location will be selected. And before the control bus, actually it sends the data through the data bus, and it will wait in the data bus. And whenever the control bus will give the signal that I want to write, then it will write the thing from the data bus to that particular address. I think it is as simple as it is.
Yes, sir.
48. Have you understood?
Yes, sir.
I think okay. Let me ask everyone. So anyone of you, should I repeat this portion?
Can you repeat the right portion just once?
Okay, in the right portion, basically you have 3 steps, but these 3 steps are not the same as your the previous read operation. So first, the address will be sent by the CPU to select the address where I want to write the data, and data is inside the CPU. So the first step is send the address. Okay, I want to save that content in that address. Then second, through the data bus, it sends the data, and the data is kept on the bus. It is on the bus from the CPU. It is now on the bus in the second step. So it sends out the data. Third, the control bus, it is in read operation that was 2, and like 2 or 3 has been swapped. Is it okay? So then whenever the control bus said I want to write, so the address is selected and data is on the bus. So it is just write on your particular address. That means that content will be saved and previous content will be erased. Is it clear now?
Yes, sir.
Okay. So then I have said earlier that what is the main purpose of having of CPU? Fetch, decode, and execute. Fetch,
Yes, sir.
decode, execute. That is the main purpose. Whether it will take decision or whatever it do, it just fetch, decode, and execute. So fetch is nothing but read. So it reads the program data from the memory. So you already know how the CPU fetch the program data from the memory. So you know from the read operation. So now for just showing you the thing, this slide has been shown before. So basically in this way, sorry. In this way, basically your data is saved in the memory. So whenever the CPU tries to read, that actually reads from this data. It fetch from this data. From these addresses. Sorry, I'm just the programs, like you have 3 lines of code that is saved in the memory. Whenever CPU wants to execute, that fetch from these addresses. Is it okay? 48.
Yes, sir.
Is it? Have you understood?
Yes, sir.
Whenever CPU wants to, the program data are saved in the memory. Whenever the CPU wants to execute or it needs to execute, it actually
It will fetch. It will fetch.
fetch the content of the addresses to the CPU. Now you can
Yes.
see just a visualization. It fetch for move AL, then what to move 05H, then it goes to execution, and it become executed. So whenever we'll go inside the box, so at that time we'll see how that is decoded and how this fetch is working inside the CPU. So just is to have a visualization where we have given that one. So it is very clear. I think it's very clear that from the memory you just fetch the data one by one. For move AL it is, and then fetch 05H, then it will be executed by the executor in the CPU. And obviously this is your CPU. Okay, this is called opcode. I will come to that point later. Just that is the machine language of move AL. Now one example has been given. Maybe the time that we tried to give, I'm out of that time. So just see. Let's see. So a real life example. Okay, it is taken from Douglas V. Hall, another book, maybe from chapter 2. So maybe we'll show by visualization or by making the diagram. So we'll show one task, this one, and other 2 will be done by you. That has been added in your lab report to do in the lab report. So what we will do, we take an input from the port 05H, that is the keyboard, and we add a value to that value that we have taken from the keyboard, and after adding we will show the output in the monitor. So how the CPU works here, so okay, here these 2 codes are basically for take the input from port 05H, and these 2 are for add 03H to that value, and these 2 are for showing the output to the port 02H. So we'll just show it things related to take input from the port, how that works. So this is your CPU, and this is your memory. and this is your keyboard, and these are the IO ports. That means inside the IO ports we have one of them is in port 5, keyboard is connected. Have you understood? 48.
Yes, sir.
Very simple. So we want to do what? First of all, what should be the first step? 48.
Sir, putting input, sir, what the command, which address I want to, select.
That means CPU wants to, if CPU wants to execute something, it needs to fetch from the address first, isn't it?
Yes, sir. We have
So
to
we
fetch
want-
the
we
data
want-
from that.
Then we'll go for execution. So we'll fetch the program from the address. So the first step to read is we sends the, this is your
Fetch.
address bus.
Yes.
This is your address bus. It sends the address from where we want to, then sends the read command that I want to read. Then from data bus, it gives the data to the CPU. Is
Yes,
it
sir.
okay?
Yes, sir.
Then the data comes to the CPU, then CPU decodes it. After decoding, it said take an input. It says that take an input. From where we should take the input, and for that reason, it again wants to read the second address. What is the content of the second address? That says that I want to read from there the steps. Try to get the steps. It sends the address through the command, through the control bus that I want to read. Then the CPU gets the data from second address. Then it gets that, okay, I need to take input from port 5. So the CPU has decided that I need to be connected, I need to read something from the input output ports, and the port is specified, that is port number 05. Is it okay? 48?
Yes, sir.
Up to this?
Yes, sir. It's okay, sir.
Now, yeah, now it sends the address of IO ports.
Yes, sir.
Oh, previously, whatever I have shown you to read from the memory, the same thing is by the same way it reads from input output ports, because CPU is the only decision maker and only operation works inside the
Sir,
CPU.
I have a question, sir. I have a
Yes,
question.
obviously.
Sir, the command of fetching the first time when we fetch a data from the address bar,
Yes.
that who gives that command first? Sir, we input our data by the input output ports, right,
Okay,
sir?
okay. Maybe I got your question. Let me give
Yes,
in
sir.
this way. Whether you have understood, let me know. So whenever you have a exe file, .exe file,
Yes, sir. Application
whenever you
file.
click that one, so that initiates a let us say a program. Okay, I need to do this.
Yes.
Oh, I'm very sorry that I'm out of electricity. Okay, let me give me just 1 minute. I connect these things with IPS.
Okay, let's while he's gone, let's discuss on the last question. I think what was the question, that who gives the this read from address and something like that, right?
Yes, sir. Yes, sir. From first command, sir. The fetching the data from the address bar.
Okay, so I mean, you are trying to physically relate it. Yeah, I mean, in real life, how is it actually working, isn't it?
Yes, sir. Exactly.
Okay, so see, whenever say you are trying to watch a movie, say, okay, yeah, you have a movie file, you just click on the movie file, isn't it? And the movie plays.
Yes, sir.
So what do you think it is doing? Is it a read operation or a write operation? Write operation, which one?
Read operation, sir. Read operation.
Definitely it's a read operation, right? So whenever you just play, your processor already knows that this is going to be a read operation. So what will it do? It will definitely access the memory where the movie is stored. So it will automatically call that address bus, hey, give me the files of the movie or give me the data of the movie. And it knows that it is going to a read operation, and it will just keep on displaying you the data. Who say you are trying to write something, say in Microsoft Word or wherever you are trying to write something. So the processor already knows that this is going to be a write operation. So whenever say it will ask you that where do you want to save and something like that, right? So you are specifying that my computer or this drive, this folder, that folder. So while write operation, I mean by yourself you provide the address. So your processor understands that okay, in this address I'm going to write something, or I'm going to save the contents that has already been written. And when you are trying to read something, you are already in that specific folder from where you want to read it. So see, by default you are already selecting the address from where you want to read your contents. Are you getting me?
Yes, sir. Yes, sir.
Please repeat. Can you please repeat, sir?
Should I repeat again?
Yes, sir.
Yes,
Please.
sir. It will be better, sir.
Okay, so like the thing is again very simple. Okay, so say you want to read, I mean you want to execute a read operation. So watching a movie is equivalent to executing a read operation. So what happens when you try to play a movie? The first thing you do is you go to that specific folder or location where you have stored the movie, isn't it?
Yes, sir.
So see, by default, you yourself are accessing the address bus. You don't know that, but you are doing that, isn't it? Because you're going to that specific address and then
Yes,
you are
sir.
double clicking it or just hitting the play button. So you are accessing the address bus by default. Then when you double click, it automatically understands that this is going to be a read operation because it can't be written. I mean, you can't write on a movie file. I mean, without some specific softwares, of course, application, those are different things. So when you
Yes, sir.
double click it, it automatically reads those things and it keeps displaying you on the output port. When you want to write something, say you have written something in a Microsoft Word or doc file or latex or whatever, you have written something. Now every time your computer will ask you that where do you want to save it. So you specify that save it in this folder, that folder, this blah blah blah. So say you are again accessing the address bus and then you are specifying that I want to save it. That means whatever I've written, please do save it. So then it is being saved. Actually the real life examples that I'm giving are much more complicated than the things we are studying. We are studying is simple read and write, but what I am saying, in trying to give you a physical real life example, we need to go to a more complex operations. But you do understand the basics, right? It is analogous to the same operations. বুঝা কি গেছে নাকি confused?
Can
Yes,
you hear
sir.
me?
বুঝা গেছে, sir.
হ্যাঁ রবিউল প্লিজ।
Yes, yes. That is the thing. Arif about explained that things are not that much simpler. Let's just
রবিউল তোর কথা আসতে শোনা যাচ্ছে। I mean previously it was clear but now it has become a little bit low.
Okay, but I am on the same microphone. Maybe I'm on IPS. That can be a reason. So, is it okay now?
Yeah, slightly better I guess. Continue.
Okay. So then I was there that whenever the CPU decided that I want to read something from the keyboard, so it sends out the address of that particular port. Then it sends the command that I want to read. Then 02. That means whenever is already okay. You can see that 0000, and after that at last is 10. That means it is basically 2 in decimal. So it is we're pressing 2, so that is giving 2 in the port. Then that will be sent through the data bus to the CPU. Is it clear? 48.
Yes, sir.
Okay, that is basically the whole operation of getting input from the keyboard. So again, if we want to do the other ones, like how to
স্যার আপনার কথা স্যার অনেক কেটে
add
কেটে
03. Yes,
স্যার আপনার কথা অনেক কেটে কেটে আসতেছে।
should I join with my mobile?
কথা কি সবারই কেটে কেটে আসতেছে? কারণ আমার কাছে কেটে কেটে আসতেছে না অ্যাকচুয়ালি রবিউলের কথা।
আমারও প্রবলেম হচ্ছে
স্যার
স্যার একটু নয়েজি আসতেছে স্যার, কথাটা
Okay, I'm joining with my mobile.
Okay, can you hear me now?
Yes, sir. Clearly, sir.
Yes, sir.
Okay, okay. So now what I was saying that other two operations like adding and showing to the monitor. So that part can you should do that part. That instruction has been given at the end. Okay. So should we go for a break for 5 minutes before moving to the next one?
Yes, sir.
Here, Sadman, are you there?
Yes, sir.
What do you suggest?
Sir, I think we can continue right now.
Because you have already got one break in this moment.
Yes.
Okay, then I'll move to 88 is not available. So 91. 91. Is he present in the class or?
Sir, he is present, but sir, his microphone has some problem, maybe, sir.
Okay, but it is showing that his microphone is connected. Okay, Sakib, 92.
Yes, sir.
Okay, you keep responding. Okay.
Yes, sir.
So whatever you have seen before, all the things are inside the box. Now we have opened up that box. The internal block diagram or internal architecture, you can say 8086. So the red line that you are seeing here, that is it 8086, your 8086. And it has two parts. So we have moved to the second part. Like previously we have seen, okay, if I summarize in first part, then we have seen read-write operation. We have seen the addresses, contents, and how the addresses are related things. Now we have moved to the second part, and here this is the internal block diagram of 8086. Is it okay?
Yes, sir.
92. Okay. So now we will show the operation. Basically, in 8086 we have two different, I should say, two different section here, two different part, BIU and EU. So this is bus interface unit and this is execution unit. For today, we will learn only BIU description. Have you got your answer? The person who have asked.
Yes, sir. Sir, bus interface unit.
Yes. So here we have two parts. So why there is two parts? Let me explain. So the execution unit executes. It is not connected to anything with outside world, like the memory. For CPU, memory and input-output ports are outside world, isn't it?
Yes, sir.
So execution unit do not get connected with those memories and all those things. But BIU is connected with BIU basically it fetches things from it is connected with the memory and it is connected with the it is connected with other things. So the buses of it is connected with input output. So that can be input output ports also. So what I'm trying to see, we'll see this diagram in the today's class and also in the next class, maybe half of the next class. So basically what we'll do, we'll try to see how this works with the memory, how BIU works with the memory and how is the execution unit works. But for today, we'll keep ourselves inside BIU. So inside BIU, if we see, we have three structures basically. Here is one. Okay, I can start from this portion. So we have different. You can see different. I should say different. These are registers. What is this? These are registers. And you can see general purpose registers. Those are present in execution unit. So what BIU do? The CPU work is fetch, decode, and what is the third one? 92? Execute. So this decode and execute part is here.
Yes, sir.
This fetch portion has been done by your BIU. So basically, BIO fetch the data from the memory.
Memory and input output.
Yes, yes. But for the time being, just we learn about memory. Those are similar things. Those have addresses and those have data. So from input output, nothing. You just take the input from the address, and from the memory, you are taking the data from the address. The same thing. Okay. So for BIU, we will see how these things are fetched. So these okay, those things will be there. But let me go to the next slide. Okay. So what BIU does, it fetch data from the memory, or the program data from the memory, and then EAU does what? It executes things. So fetch, and the EU is basically execute things, and BIU is connected with memory and input output things. Okay. Before going to there, so we need to learn about memory segmentation, because all these registers that you are seeing here, if we want to explain all this portion, then you need to know the memory segmentation. So just maybe 2-3 minutes or few more minutes for memory segmentation. So you can see, let us assume that you have written a book that is start with chapter number 0, then chapter number 1, chapter number 2. Each of the chapter has 10 pages. Is it okay? 92.
Yes, sir.
So you have two numbering page numbering system. One is the chapter pages. It is 1 to 10. Another is your book page numbers. So it starts from for this it is 1 to 10. For it is 11 to 20. So it is 21 to 30. So if I say, let us select this one. Oh, sorry. Okay, it is that one. I do not. Okay, 8. What is the page number in terms of that chapter? So if I say what is this page?
This means page 8 from chapter 1 and page 18 for book.
Yes. So that there is a page number and overall page number. So for this one, the page number chapter 1 page 8. What is the overall page number? That is 18. So how can we calculate that 18? That is basically your chapter number. We have chapter 0 there, chapter 1 here. So for chapter 1, it is 1. Then we are multiplying with 10. Then we are adding that page number of that particular chapter. So that gives us 18. That is the overall page number. Okay. Now, this is analogous to our, for 6 and 26. Should I ask any other, or should we proceed? 103, Tawqir Shahriar.
Yes, sir.
So what is the, can you explain that has been selected here? Chapter number 2, we have selected one page. What is the page number of that chapter, and what is the overall page?
So the page number of the chapter is 6 and the overall page is 26.
So how can we calculate 26?
We can calculate 26 like the before, it's 2 into 10 and plus 6.
Okay, thank you. So the same thing, 2 into 10, 26. Now the memory. Beforehand, I have said that your memory is of 2 to the power 20. Try to connect all those things, what we have learned. So, but your 8086 is a 16-bit processor. What have I said? 92.
So 16-bit processor.
Yes, I'll explain that part. 8086 is 16-bit processor. That means, if I go here, this ALU, what is ALU? 92. Do you know what is ALU?
No, sir.
Anyone?
Arithmetic logic unit.
Yes, arithmetic logic unit. So it can process at a time 16 bit of data. So the 8086, it has the data bus of 16 bit. It can process. It can execute. What should I say? There are so many phrases that can be added here. So it can transfer. It can work. It can operate with 16 bit of data. But our address bus is of 20 bits.
20 bits.
Have you got my point?
Yes, sir.
So our 8086 is 16-bit processor, and our address bus is of 2 to the power 20. So it will be better for us if we can express that 20 bits of addresses into 16 bit of addresses, isn't it? So that is the procedure we are going to have. So what I'm trying to say, our 8086 can process work, operate with 16 bit. That's why it is called 16-bit processor. But our address bus is of 20 bit. That means if we can express, like the Arif has said beforehand, that if you have a folder, you know that folder name, that this name, subfolder, then you go into up to that video file. So you know that folder number, but the computer doesn't know that folder. That is not the actual physical address. I have said at the beginning that 20 bits of address, that means in hex that is 5 bits, and in binary it is 20 bits of address. That is the physical address.
Yes, sir.
So whenever you are saving something to a folder, that is your virtual address actually, isn't it?
Yes, sir.
So basically, if you want to access any data, try to get this point. If you want to access any data, you need that physical address. You need that physical address to access any data from any address. Now, we want to express that 2 to the power 20, that means addresses, that means 20-bit addresses into 16-bit address. So how should we do that one? So if we just we have 2 to the power 20, so we can rewrite to the power 4 into 2 to the power 16, isn't it?
Yes, sir.
So 2 to the power 4 is how much?
16.
16, and there is 2 to the power 16. That means we can have 16 segments of memory which can be accessed by okay, I am coming to that one. So if if you want to have 16-bit address, what is the minimum address that can have? 0000, isn't it?
Yes, sir.
So each of these segment basically starts with 0000 and ends with FFFF.
Just a second. That
Yes,
0000 is in hex. Okay, so don't get confused.
Yes. In total, there is 16 bits.
Yes, sir.
Yes. So this is each of these segments. Okay, we have RAM and ROM. We are talking about RAM. We are not going to the mapping of the memory. This is just few segments of the memory. So we are not talking about ROM. We are not talking about other parts of the RAM. So we are talking about some parts that is related to CPU execution and BIU. So we are talking about those things. Is it okay?
Okay, sir.
So each of these segments starts from 0000 and ends at FFFF.
FFF. Yes, sir.
And obviously it is H. Now, how many segments can be there with 1 megabyte of memory? So it is your 1 megabyte memory.
Yes, sir.
Your 8086 has 1 megabyte of memory. So how many segments is possible with this 1 megabyte of or how many segments of okay, to the power 16? How can we express to the power 16? To the power 6, then to the power 10.
10.
That means 64 kilobyte.
Yes, sir.
Isn't it? So I want to ask this question, that how many segments of 64 kilobyte is possible with 1 megabyte of data, 1 megabyte of addresses?
16.
Yes. That's what I want to get from you. So is it okay? You are dividing that one to the power 4 to the power 16. That to the power 16 is basically your 64 kilobyte.
Yes, sir.
So this 64 kilobyte can be accessed. This 64 kilobyte address can be accessed with this 16 bit of data. That means from 0000H to FFFFH. That means you can have 16 segments, out of which we have selected this is data segment. In short, we say DS, CS. This is your stack segment and extra segment. Is it okay?
Yes, sir.
Okay. So if I say what is the purpose of this these segments in code segment, the program is saved in the code segment. Have you got my point?
Yes.
The program is saved in the code segment, and different data like your the random data or the data that we do not need to execute, or those things, the different data like you want to just save a movie, so that data or that video can be saved in data segment.
Yes, sir.
Or that is the thing, or you have a variable in the code that can be saved in the data segment. So what I'm trying to say, the code segment saves the code, so data segment and extra segment saves the data, different data, and stack segment has a special purpose. Maybe have you heard the term stack before?
Yes, yes, sir.
So it is nothing like the storage that has a particular. Obviously, we set aside a stack segment. Sometimes, if you want to perform some task, and also it is used by the CPU, and a programmer can also access that segment.
Extra memory, sir.
Extra memory, and that not extra memory. Stack segment has a special task. You can say the first in, last out. Have you heard the term?
Yes, sir.
Yes, that is the stack. So you want to save something in the stack segment. The last thing that has been saved, that will be popped out first. That will be popped out first.
Yes, sir.
Okay. Now, before going other portions, so this code segment, now we have this code segment has been enlarged here. Okay. So this is your physical address. This part your physical address. That means you can see 20 bits. In hex, it is 5 bits.
Yes, sir.
Okay. So what is that? 3488A.
Yes, 0.
And there is a 0 there. So in every start of any segment, this last bit will be 0. That means if we say in last 4 bits of 20 bits, it is a 20 bit of a physical address. So last 4 bit will be 0.
Yes, sir.
Of every segment. And the upper 16 bit in hex, upper 4 bits, like okay, I should say 16 bit. So this is saved in CS. That is a register. Is it clear? 92.
Yes, sir.
Can you tell me what I have said?
Sir, every segment, the starting one is 0, sir. So this
not starting. This is the least significant, isn't it?
Yes, sir. So
the last 4 bits, that means last 4 bits of 20 bits of data, that will be 0.
0, sir. So then the baki portion, sir, register CS se save hoga, sir.
So this is code segment.
Yes, sir.
So that starting address, the first 16 bit of that physical address, starting of that, this is the start, isn't it? So that 16 bit of data will be saved into the register CS. So these are registers. Note the segment. Segment is in the memory, but okay, I'll go to that part later. But try to remember the CS is the register where the first physical address is saved. Is it okay?
Yes, sir.
Now there is IP. It is called instruction pointer. What is that? Instruction pointer. It is a register where the offset address is there. So it starts IP address is basically in between 0000 to FFFF.
Sir, I didn't get IP, sir.
Okay, just a minute. So I have said that each of these segment will start from 0000 and ends at FFFF. So you have the physical address, this one. You have the code segment register, which has the upper 4 bytes of the physical address. Now, if for accessing different positions, we have different, I should say, let us say for code segment, it is IP, it is a register. And for stack segment, it is SP. stack pointer. Then for extra segment, it is the register is DI, and for data segment it is SI. So these are the pointers by which we can determine 0000 to FFFF, in which location we can determine by IP. So here in code segment, so it is start from 0000, the IP start from 000 FFFF. Let us say we have a data here, so we can say in code segment we have the data at 4214H. Is it okay? These are the chapters: code segment, data segment, stack segment, extra segment. These are the chapters, and this is your page number of that particular chapter. This is the page number of that particular chapter, and physical address is the page number of overall book. Is it clear now?
Yes, sir.
So code segments, data segment, stack segments are different
chapters.
These are the different chapters. Physical address is the page number of the book, and IP from 00 to FFFF, these are the page number of that particular chapter.
Yes, sir.
Is it okay?
Yes.
So why we are going to the page number of
the memory section segmentation again?
Yes, sir. Please, sir, can you repeat memory segmentation again, sir?
From the beginning?
Okay, just a second. I think, Ravi, let me add a very few things. Okay.
Okay.
So let me try to explain also. So did you understand the previous example where we had 3 chapters? Each chapter had 10 pages.
Yes, sir.
And overall we had 30 pages, right?
Yes, sir.
So say someone is trying to read that book, but he can count only from 1 up to 10. He doesn't know what is 11, 12 and something like that. Okay. Now, say he is trying to read chapter 2, page 3. So physically, what is that page number? That is 23, isn't it? We already know that.
Yes, sir.
Yes, sir.
See, he doesn't know 23. What he knows? He knows only from 1 up to 10. So how can he say which page he is reading? So he will say that I am reading chapter 2, page number 3, right?
Yes,
Yes, sir.
Is it okay up to this?
Yes, sir.
So see, that is the limitation with our 8086 processor. It says that it is 16-bit processor, but the address we have is already 2 to the power 20. So the 16-bit processor cannot access that,
physical address.
Physical address. It cannot access that. So in order to overcome that problem, what are we doing? We are dividing our entire memory into 16 segments, which is equivalent to our chapters of the previous example. Is it okay now? So we are having now 16 segments. Now in this segment, say you have got a particular segment named code segment or something like that. So in that code segment, say the address is at 4214H. The example which is given over here. So see the 16-bit processor does not know the entire physical address. Like the exact address will be 38AB4H on your left hand side. Okay, the exact physical address. So your microprocessor does not know that. So what will it do? It will say that in code segment go to 4214H, isn't it? That is what it can do. But so how can you convert that into physical address? You have already seen a previous example. So you know that to convert that, we simply multiply 10H with the chapter, and then we add the page number of that particular chapter in which it is in. So in that particular code segment, we are in page 4214H. So at the end, we will simply add 4214H. And if you are in chapter 2, you multiply 2 into 10. So now you are in code segment. So code segment is equivalent to 3481, which Robul was discussing, that the first 4 bytes or first 4 bits. So that will be multiplied by 10H, and then you will add the IP. IP is equivalent to the specific page number where you are in now. Is it okay now?
No, sir. Can you repeat it again, sir?
Which part?
এই যে স্যার আইপি তে যে ঢুকলেন স্যার এই যে স্যার 348A0H এরপর স্যার আইপি দিয়ে
okay, just a second.
I'm clear about the 16-bit
wait. 179, are you present? Wait. Abdur Rahman, are you present? 179?
Yes, sir.
Okay. So try to concentrate, okay?
Oh. He can mute after 179. Please mute yourself.
মিউট করে দে Okay, so you are confused about 4214. Is it that IP?
Yes, sir.
Okay, so take the example of the previous one. So someone is in chapter 2, page 3. So his IP is 3. Okay, so say he is in page 8 of chapter 2. So now his IP is 8. So in a particular chapter, in which page he is currently at is the IP. I mean, this IP is definitely variable. It will vary every time. It totally depends which page you want to access, but it will be within that limit. I mean, for the previous example, your IP will be always between 1 to 10. In this particular example, your IP will always be between 0000H up to FFFFH. IP will be anyone between this. That are the page numbers between which that particular chapter is distributed. Are you getting me?
Yes, sir.
So if you are reading, say, page 7 of chapter 2, what is your IP?
Sir, 7.
Yeah, simple, 7. So in this particular example, say someone is trying to access 4214H memory location of the code segment. So what is his IP?
4214.
Yeah, simple.
Yes, sir.
Simple. So is it clear now?
Yes, sir. IP পর্যন্ত clear, sir.
IP পর্যন্তই দেখাইছে, আর কি দেখাইছে?
Okay. Thing is that after whenever you're getting the IP and you know that the starting of you have the value of CS. Let us say you have the value of CS. What is the value of CS?
Yes, sir. I have another question, sir.
Okay. Just before that one. So what is the value of CS? I have said CS is a register, and if you have a physical address, the first 4, isn't it?
Yes, sir.
Can you remember that part?
Yes, sir.
I do not know why is this switching. Okay, then if this is your CS and this is your IP, there these two the value that you have, the chapter number and the page number. Code segment is starting of the code segment, the upper 4 values and your offset values. Now you multiply 10 with this one and add this portion. That means you are going to that particular location, that particular address. Now someone is asking something.
Sir,
Someone
why
is asking.
are we multiplying by 10?
Why are we multiplying by 10?
Yes, sir.
So that is the same thing that I should say, that why have you multiplied 10 in the previous case? That was in case of your.
Sir, there were 10 pages per chapter, but
Yes,
here why are we multiplying it by 10?
Okay, why are you multiplying with 10? In that case, okay, I actually do not know the inner thing, but what I understand is that we have 4 bits, and then in the so this works like this: 8484A, then 0, and so in the first IP is your 0000. So that has been added. If we add that one, that will go to a particular portion, and then if we increase from 1, then 2, then FFFF, all these things will be added to this portion. Okay, so that is what should I say? Let me keep it for the next class. Why actually we're multiplying with 10? So obviously I have not gone through that one, obviously, but this is the thing that whenever you are adding, you're multiplying, that is adding 1 bit here, and then you are adding that IP. So if I write it here fresh, so the first IP is your 0000, then it can be anything from 0000 to FFFF. If we add, then we get a physical address of 5 bits. That means in total 20 bits. So is it clear up to this? Like I will say, I will discuss about 10H later. Other than that, is it okay?
Yes, sir.
স্যার আরেকটা কথা স্যার, আমরা স্যার 348 এ 0H আছে, আমরা শুধু কেন 348 এ নিলাম মানে মাল্টিপ্লাই করার সময়?
So the CS will contain this is the register. So these registers are also 16 bits.
Yes, sir.
So That's what I'm saying. The last bit will always be 0. So this is the starting of your code segment. Is it clear?
Yes, sir.
This is the starting of the code segment. So CS is a register. So let me show you there.
Sir, are you there, sir?
Wait. I think Robil got disconnected. Just
Yes, sir.
wait.
Sorry, I just got disconnected. Sorry for that.
Robil, there was a question like why are we multiplying with 10h? So I think I can try to answer that.
If you are sure, you can proceed.
Okay. আর রবিল তোর কথা এখন আসতে শোনা যাচ্ছে রে, পারলে ফোন দিয়ে ঢোক।
Okay.
All right, so the question was why are we multiplying it with 10h, isn't it?
Yes, sir.
Okay, so I will always give examples which is related to that book and chapter. Okay, I think because that is the part we all understand very clearly, isn't it?
Yes, sir.
Okay, so say you have got you have got 100 page of a book that is in total it will be 100 pages, but the person who is reading, he can read only from 1 up to 10. All right, is it okay up to this?
Yes, sir.
Okay, so he can read only from 1 up to 10. So in that case, I mean, how do you decide that with what you will multiply, or I can also say what will be the maximum length of a chapter, or how many chapters will be there? I mean, all these things are the same thing I'm asking. So okay, let me rephrase it. So you have got a book of 100 pages and the maximum number the person can read is 10. All right, so how many chapters will be there?
10 chapters.
All right, so there will be 10 chapters. Okay, so if there are 10 chapters, every time for one chapter, I mean, what are you multiplying with each chapter?
Sir, multiplying with 10, sir.
Exactly, so it depends on the number of chapter, or we can conversely say, how did you get 10? You simply divided 100 by 10. I mean 100, that is the total number of pages of the book, divided by the maximum number he can read, isn't it?
Yes, sir. Yes, sir.
Right? Okay, now let us come. What is the memory address in 8086? That is 2 to the power 20, right?
Yes, sir.
Yes, sir.
Okay, so we are always representing all these things in hex. So in hex, what is the highest physical address? By physical address, I mean the total number of pages, not chapter wise, the total number of pages. So what is the highest physical address you can have?
FF.
How many Fs?
There are 4 Fs.
Is it 4 Fs? Physical address. I'm talking about physical address.
Physical address.
I mean the entire address.
5F.
The page number. Exactly. There can be total 5 F, right?
Yes, sir.
Is it understood up to this?
Yes, sir.
And what is the highest number in hex that your microprocessor can read?
4F.
4F. So in analogous to the previous example, what should we do now?
We need to divide, sir.
Exactly. If you divide in hex, your answer will be 10H. Simple. And in decimal, it will be 16. That's why you have got 16 registers, and that's why you are multiplying with 10H. You can try and convert 10H into decimal, you will get 16. Equivalent to the number of chapters or equivalent to the number of segments that we have. Did you get your answer or you are still confused?
16 to 10, 8 একটু আরেকবার একটু বলুন স্যার প্লিজ।
Is there anyone with a calculator?
Yes, sir.
Okay, go to your base mode. Go to the base mode. Yes, sir.
Yes, sir.
Okay, see over there in your calculator, there is a button that says hex. So click on that. I mean, go to the hex. In base mode, go to hex.
Yes, sir.
Okay, now write FF. I mean, write 5 Fs. I mean, there is a F over there. Just simply press that. I mean, equivalent to 10, I think. Just write F. It will write F. So
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Now divide by 4 Fs. Right? Divide and then write again 4 Fs. F.
Yes, sir.
Now click equal. What is the answer you get?
Sir, 10. Yes, sir.
So that is your hex. So
Yes,
you
sir.
convert that. Now click decimal. You will get 16. Click on decimal. It will show you the corresponding number.
Yes, sir.
So is it okay? Now why we are having 16 segments of memory? Why you are multiplying with 10H? Is it clear now, everyone?
Yes, sir. Yes, sir.
Any question? Anyone else? এইটুক বোঝা গেছে?
Yes, sir.
Yes,
So,
sir.
so I hope that now if we have a starting address like the data in CS, and if we have a offset address, that means segment address and offset address, then we can get the physical address from there using this particular formula. Your segment register, what is it? It has a 16-bit of data, multiply it with 10H, and then offset address, it is also 16-bit data. Then if we add all those, then we will get physical address. Is it okay? So why we need the physical address? Because to access any, the memory doesn't have these virtual addresses. These are not known to that particular memory. So memory has the physical address. So if we want to access any data of that memory, we need that physical address. Is it okay? So okay, I'll explain that. Okay, here before so you have code segment, you have IP, CS, IP. What does the CS having? CS having the starting address. Let us say it is of 20 bits. The first 16-bit, that means most significant 16-bit, has been saved in this register. It is not directly the code segment. It is a register that saves the starting what? Starting address. So using this CS and IP, if we just multiply CS with 10H and then add your IP, then that will give you the physical address of that particular address that is pointing by your IP. Let us say your IP is here.
Offset টা কি actually IP টা?
Yes. The offset address is the IP. So for different, I have shown in previously that for different segments, there are different pointers. For code segment, it is IP, instruction pointer. Is it okay?
Sir, why we have only 4 segments here? Isn't it, shouldn't it be 16 segments?
Yes, there are, I have said that there are, you have RAM, ROM, and BIOS. You have heard about BIOS, isn't it?
Yes, sir.
And also this 1 byte memory has both RAM part, ROM part. So we are not discussing all about those things. and there are other things that is needed for the CPU to proceed, like interrupts vectors are saved in the memory. All these things are saved in the memory. As we're discussing this part, this part only needs these 4 segments, and that is related with the CPU for understanding the operation, fetching, decoding, and execution. We are just confine ourselves with these 4 segments. Is it okay?
Yes, sir.
Okay.
Sir, are these 16 segments all part of the code segment or extra?
No. 16, out of 16, we have only 4 here.
So
out of 16,
every segment has different names like this.
No. Okay, for memory mapping, maybe I will ask Farhad to add that memory mapping in the next lab. You will see that the whole 1 megabyte has been divided into different parts. You know, basic input output system, the BIOS. Whenever your system, whenever turn on your computer, that first of all it takes the command, takes the codes from the ROM part, that is read only, that is not deleted. From there, your system is booted. So that is also a part of the memory. Is it okay?
Yes.
So maybe we'll have that part just to show the memory mapping. Okay. Now about the IP, you are saying about the IP. So this statement clears everything. IP hold the offset of next instruction. So if this is executing, IP address will be pointing towards the next instruction. Have you got my point? IP always. So how do you know that what will be our next instruction? You have move AL, then you have this 3 instruction. How do we know what to fetch?
By using IP.
By using IP, yes. Whenever you'll be having IP, that you can fetch that data. So IP is always it holds the offset address of the next instruction. Is it okay? So what we are trying to say, using this CS and IP, this is another arithmetic circuit that actually do this math and find out the physical address and sends it to the memory. For this, actually, we have all this discussion just to understand this portion, that we have CS and IP. IP is always in the next, pointing to the next one, and it takes, it sends this, it creates the physical address using this particular formula, and then after calculating the physical address, that is sent to the memory from where we want to fetch. So what we are fetching? IP is always pointing to the next instruction. So we are fetching the next instruction. Whenever the current instruction is going on here in EU execution unit, we are fetching the next instruction. So after fetching the next instruction, we will fetch the next to next instruction. Is it okay? Have you understood? Okay,
Sir,
I was
how the next instruction is being instructed? Sir, next instruction part ta buchi nai.
Okay, I was saying like there you have said the 3 lines of codes, isn't it? Okay, previously. So it is a 3 lines of code. Whenever it is executing in the execution unit, or whenever you have fetched this one, for execution. You have fetched for execution. So what will be our next one? So IP is the address, isn't it? It always points to the address of the next instruction. This is our first instruction. This is our second instruction. This is our third instruction. So IP will, so whenever you will fetch this one, so IP will go to the next one. Have you got my point?
Yes, sir.
Yes. So that is the purpose of BIU, that using that CS and IP and using this arithmetic circuit, it addresses, it makes the physical address of the memory, and then it fetches that one. And after fetching it, then our second architecture is this 6 byte of prefaced queue. We'll talk about this now. So up to this, is it clear? So that has an animation, like you can see all these things. Maybe that will not take much time, but have you understood this part? Anyone, have you any confusion? Okay, no one is replying. So 98, 98.
Yes, sir.
Have you understood up to this?
Yes, sir.
Okay. So, so one question has been here: why we need two arithmetic circuit? So we can have the question that, okay, so we have the ALU, arithmetic logic unit, so we can send CS and IP there, and we can add and do all those things. But thing is that we are doing pipelining. That means we are executing one thing, and that execution need ALU, and also you are fetching the next instruction here. So for that cannot be using. So we can use these two as simultaneous way. Like we can fetch, you can execute at a time. So that has been shown in here. So let us say you have memory. From memory, you are getting the instruction for execution, and after that, after executing, you are requesting the memory to get the next instruction. So this is one scenario. Another scenario is that from the memory, you are fetching to BIU. That one execution is going on. One execution is going on in the execution unit. One has been fetched from the memory. So whenever you are, so this is your from the memory. So whenever this execution will be done, the first one, this was your first one, this is your second one, this is your third one. So whenever first one has been executed, from BIU we can directly get the next one. We need not to ask the memory to get all those things. So whatever the thing you have seen in here, so basically it is pre-fetching, like it is fetching for the execution unit. So it is keeping the fetched program from the memory so that the time requires is less. So just tell me, in these two situations, which one will need less cycle? Obviously, all the microprocessors have the cycle. So we have executed something, and after execution, we are asking the memory to send. And here we have BIU and execution. So while you are executing something, we are getting the next program from the memory by the BIU. So which will take less time? Second one, isn't it? So that is the thing that we are doing. We're pipelining. We're getting the, because it takes more. What should I say? More cycle to fetch from the memory. So if after execution we are asking the memory, that will be a loss of few cycles will be lost there. So that will not be a fast process. So that's why BIU is fetching the program data from the memory beforehand, before going to execution, so that the execution unit inside BIU and execution, those are the part of the CPU, inside the CPU. So whenever BIU gets the data from the memory, those needs interfacing between the memory and the CPU. But whenever execution EU wants to get data from BIU, it gets inside. Okay, so.
Sir, why is it called BIU, bus interface unit?
Okay, name can be anything, but what I understand is it is interfacing with the memories and also input outputs using the address bus. So it calculates. Its main task of this one is to fetch. That means it needs addresses of input output port and memories. So in that sense, we can say the bus interfacing. That is interfacing with the memory unit with the buses. That can be a thing, but you can give any name, but this can be an explanation. Is it okay? Main thing is it sends the address from where you want to fetch. So all the outside works are done by this BIU, outside world tasks, like connecting with others and connecting with also the input output and memory. Those are done by BIU, but EU is not connected to any one of these memory or input output. Is it okay?
Sir, for the next instructions IP,
yes.
Does the BIO get it from the execution unit or from the memory? Because from the arrows we can say the arithmetic unit goes from BIU to memory, and there is another arrow from EU to BIU.
Yes. So just try to get this. All these are saved. You should say those are saved serially. Like you have first instruction, saved from, let us say it is your first address and this is your sixth address. So all these programs are saved serially. So whenever you fetch the first one, the AIC will instruct to the next one. And also IP, if there are control buses connected to each of every part of this BIU and EU. So basically, those signals are given by the control system. But try to understand that all these programs are saved serially from, let us say, from 100H to 101, 102, 103. So let us see in the next couple of slides. Maybe that may be clear. Okay, now we can say it is saying the fetching and execution is done simultaneously. Okay, I have what are these? Okay, I have explained much about all those things, and maybe you have understood all those things. And address bus, I have said much about those things. Address bus is 20, and control bus is of 16-bit, and data bus is of 16-bit. And also your ALU can the 8086 is 16-bit processors. Okay, so now we want to learn this 6-byte preface queue. That means it has 6 bytes, means each of them is 1 byte. So we have a 6 byte of memory inside the CPU where this program can be prefaced. So our option is we can save just one instruction here, or we can save several instructions here. So there are 6 bytes here. So we can fetch 6 bytes of program data inside the CPU. Is it okay? Anyone? I have lost that serial. So anyone? 134.
Yes, sir.
Have you understood this part? That we can fetch the program data and save it to 6-byte preface queue, so that we can directly take that from BIU to EU.
So is it like a temporary memory
Yeah,
inside BIU?
temporary memory means it is a memory that has the preface program data. That means we can fetch one by one. But if we have a 6 byte of data, then obviously we can state why. You can ask that why this 6 byte. So then I should answer that the maximum. Okay, so before going to that one. Okay, before going to why 6 bytes, then we have queue and stack. Maybe you can just see these 2 slides. Queue is basically first in, first out. So this is your first that has been inserted here. Then that will be out first. So it has been out first. So that is the queue. But in case of stack, basically first in and that will be out last. That is the stack. So I think queue and stack is clear.
Yes, sir.
Yes, sir.
Okay. Now, why 6 bytes? That's the question. So to understand this, we need to know size of an instruction. So previously we have seen move BL, 05H. So how many bytes of data does it need in machine language? So that is the instruction size of the instruction. If it needs 2 bytes, then this 2 bytes is the size of the instruction of this one. Is it clear?
Yes.
Okay, now. So here we have given one example, instruction size. So increase BX, it has just 1 byte of instruction. Like whenever we'll transfer that, these are all are the machine language. And these are our assembly language. Whenever we transfer that machine language to our, okay, for this, so for increase BX, we have 1 byte of, this 1 byte instruction. So nope is also 1 byte instruction. You can see here, move is of 2 byte of instruction, and move CX, 008 is of 3 byte instruction. So the maximum, in case of 8086, the maximum size of an instruction is 6 bytes. Is it clear? So we can fetch, so that we can fetch the whole instruction together in the prefaced, that is the maximum, the preface is of 6 bytes. You can see in the previous case, it is of 6 bytes, preface queue. So a maximum size of an instruction of 8086 can be of 6 bytes. So the whole instruction can be saved here. We do not know how many instructions are there. It depends. So if we have like in the previous, in the next case, you can see here, you have your increase. It is 1 byte, is 1 byte, is 2 byte, and this is 3 bytes of code. Whenever we'll be doing the code, we can see all these things, or we can see the machine language. How this single line code is how many bytes of machine language. Is it clear? Have you understood?
So one instruction can be maximum 6 byte.
What instruction? Okay, that we will see that one. We'll see that one obviously, but you do not know all the instructions yet, isn't it?
Yes, sir. I'm asking, is one instruction 6 byte or
which one? Which one? No. One
so
instruction.
Here,
I am saying that you can see the variable. The increase bx is an instruction which can be translated to machine language by 1 byte. Nope is an instruction which can be translated in 1 byte. Is it clear?
Yes, it is.
And this particular can be 2 bytes. This particular is 3 bytes. These are practical examples. So there is an instruction which is of 6 byte maximum. The maximum instruction that 8086 have is of 6 bytes. Is it clear now?
Yes, sir.
Okay. Now maybe we are at the end. So thing is that now we have a 6 byte prefaced memory here inside BIU. Now if we want that, okay. Now this is your execution unit. This now from the preface data, we'll take data to execution unit. Now when we'll take the data, next data from the memory, because BIU will be fetching. So let us say initially the queue is filled. Now one data has been taken. So there is 1 byte is vacant. So should the BIU take data or fetch data from the memory to fill this 1 byte of data? 134.
So if it is one byte instruction, maybe then.
If it is 1 byte instruction, then yeah, okay. Then any other answer from anyone? So we have a hint in the slide.
No, sir, we can actually take any because it's queue and it will go serial.
It will go serial. So if one is vacant, you are saying that another can be taken from the memory.
Yes.
Okay. Any other opinion? Any other saying from others? Anyone? Okay. Basically, thing is that our data line is of 16 bit. We have learned that one. The data. Obviously, this will be coming through the data bus. We'll select the address by BIU. Okay, this particular one. But that particular content will be fetched through the data bus. So data bus is of 16 bits. So at a time we can take 16 bits from the memory, from the program. So whenever 2 of these one will be vacant, then we'll fetch the next thing. So at a time, when 2 will be vacant, in that case, we'll take 2. What should I say? 2 content or 2 bytes of data from the program, from the memory. This is the memory. From the memory, we'll take directly 16 bit of data. Because if you take 8 and 8, but you have the capacity to take 16 at a time, so why should you lose one cycle? Is it clear?
Yes.
Okay. Now actually we're at the end. So whenever 2 will be vacant, so the next 2 will be coming from the with the 16-bit data line. So when next 2 will be vacant, then those 2 will be coming from the data line. Is it clear, everyone? I want to ask everyone. I think obviously it is a long class. But we have started at 10:40. It is 12:40 now. Almost 2 hours of theory is very difficult, obviously. Now, what is the drawback of pipelining? You try to search this one. This is your home task. There is obviously a drawback. That means whenever we need to jump, there is a jump command or branching. You can. I'm just quoting these two: jump and branching. So you can search that one and you can find the drawback of pipelining. Okay. I think this is the end of.
Robiul, I think 88 wants to say something. Alavi.
Yeah, obviously, 88. No, he is in the bus, I think.
Or microphone সমস্যা কিনা যায় না chat দেখ chat he wrote something in the chat.
I cannot see the chat.
Sir, can you hear me?
স্যার ও হচ্ছে যে প্রবলেমের জন্য গ্রামের দিকে যাচ্ছিল, আমি বলছিলাম ক্লাসের শুরুতে আপনাকে।
Yes, but he wants.
After the class ends, I will talk to you, sir. You can continue the class.
Okay. So the your home task should be in handwritten form and submit the PDF form. Take the picture and for the first lab, obviously that should be a handwritten form. These are given, and obviously these. I think we will upload the PDF form, and it is open source for everyone. If you want to ask anything from anywhere to this class, or if I want to summarize, then we have learned the address of memory. Then we have learned about different segment. So we have learned about the memory basically. So address, then segments, and inside the CPU we have seen the architecture, and architecture we have discussed about BU. Maybe in the next class we'll go for EU, execution unit, how one instruction is executed. And also in BIU we have learned there is two tasks basically it does. It basically one fetch, and to fetch it needs to calculate the physical address, and after calculating the physical address it sends the physical address and through the data bus the content comes and saved in 6-byte prefetched queue. So I should say that is the summary of today's lecture.
I think I was supposed to ask few questions, but I think we are running short of time, and also I'm having some construction problem in my building. So on the next lab, at the very first 10 minutes, I will ask some questions randomly to some people, and that will be your class performance for today's lab. Okay?
Okay, sir.
So if you have anything to say from anyone, and
could you hear me? Sorry, because there was too much noise. Could you hear me, everyone?
Yes.
Hello, sir.
Yes. 88.
Yes, sir. Sir, one of my grandmother is really sick. Like she's in a serious situation.
Yeah,
so I need to urgently travel to the village. So I was.
The CR has already informed me. So no problem.
So next class, I will collect the resources from the internet. I'll do the class performance.
Okay. No problem.
Sir, I was facing load shedding, sir.
Maybe some of you have already messaged me. Okay, no problem. Okay, anything else? Anyone? So 99, Ashikur Rahman. 99, are you here?
Yes, sir, I'm here.
So have you understood the lecture?
Not full of it, sir, but I will just again I got the try to catch it up again.
Okay.
I was not here because my family is sick. My family is sick. We are corona positive, all of us.
Okay.
Thank you, sir.
Okay. May Allah help you.
Thank you, sir.
Then 109, Riyaz Salehin.
Yes, sir.
Saledin. Have you understood at least most of the part? Obviously, it is difficult to catch all this stuff.
Some parts are a bit confusing to me, but I guess I can search up the internet to find out.
So my suggestion, yes, you can search the internet, and obviously you can go through chapter 2 of Douglas V. Hall. So related topic of that one, Douglas V. Hall. Maybe I can I have few pages pictures of the pages. Maybe I can supply it to you. Maybe by today I'll upload that one. Okay. I hope there is nothing in chat. Okay, thank you. Anything else?
Sir, assalamu alaikum, sir.
Walaikum assalam. You can leave. Thank you.